There is a continuous time system which is given as y of t is equal to t plus 4 multiplied by x of t minus 1. We have to find if the system is linear, time invariant, causal, stable, memoryless, and invertible. We see that the given system satisfies superposition principle. From this, we can say that the given system is linear. We can also say that in this case, the output due to delayed version of input is not equal to delayed version of output. From this, we can say that the given system is time variant. Also here, the output at any point of time, that is y of t, depends on past x of t. From this, we see that the given system is causal. Also, the output at any point of time doesn't depend on the present x of t. It depends on the past x of t. So from this, we can say that the given system has memory or it is not memoryless. Also, if we assume that if there is a bounded input given to the system, that is mod of x of t is less than or equal to bx, we can show that mod of y of t is equal to mod of t plus 4 multiplied by mod of x of t minus 1, which is which tends to infinity as t tends to infinity. From this, we see that if there is a bounded input given to the system, the output is not bounded. From this, we see that the given system is not BIBO stable. Also, we can show that if we try to get the inverse system of the given system, we can write that x of t minus 1 is equal to y of t divided by t plus 4. Replace t minus 1 by t, we get that x of t is equal to y of t plus 1 divided by t plus 5. So from this we can see that for any obtained output we can recover x of t back if t is not equal to minus 5. If t is equal to minus 5, we see that x of t would tend to infinity and we cannot recover y of t for the sorry we cannot recover x of t for any obtained y of t. From this we see that the given system is not invertible. Now let us consider another system, that is y of n is equal to n minus 4 multiplied by x of n. We have to find if the system is linear, causal, memoryless. We see that the given system satisfies superposition principle. From this, we see that the given system is linear. Also, we see that the output y of n depends on present x of n only. Means it doesn't depend on future x of n. From this, we can see that the given system is causal. Also, we see that the output at any instant depends on present x of n only. So, from this, we see that the given system is memoryless. So, we see that the system y of n is equal to n minus 4 multiplied by x of n is linear, causal, and memoryless. Now, let us consider a discrete time system which is represented as y of n is equal to sine of 5 by 6 by n multiplied by x of n. We have to find if the system is linear, time invariant, causal, memoryless, stable, and invertible. We see that the given system satisfies superposition principle. From this, we see that the given system is linear. Also, we see that in this case, the delayed version of output y of n minus n naught is equal to sine of 5 by 6 pi multiplied by n minus n naught as a whole multiplied by x of n minus n naught, and the output due to delayed version of input, that is x of n minus n naught, transformation of x of x n minus n naught is equal to sine of 5 by 6 pi n multiplied by x of n minus n naught. As these two are not equal, we see that the given system is time variant. Also, we see that the output y of n for every n depends on present x of n. From this, we see that the given system is causal. Also, as the output depends on the present x of n only, the system is memoryless as well. So for checking the stability, let us assume mod of x of n is less than or equal to b of x. So from this, if we try to find mod of y of n, that would be equal to mod of sine of 5 by 6 pi n multiplied by mod of x of n. We know that this is definitely less than or equal to bx, because mod of sine of 5 by 6 pi n is less than or equal to n, and mod of x of n is less than or equal to bx. We see that for a bounded input, the output is also bounded. From this, we see that the given system is VIBO stable. Now, for finding the inverse system of the given system, if we try to find out x of n in terms of y of n, we get that x of n is equal to sine of 5 by 6 pi n multiplied by x of n. Sorry, multiplied by y of n. From this, we see that for any obtained output y of n, we can recover the x of n back if 5 by 6 pi n is not equal to pi k, where k belongs to z, because for these values of 5 by 6 pi n, the sign term will be 0, because of which x of n tends to infinity. From this, we see that the given system is not invertible. Now, let us consider another problem in which there is a signal x of n which is given as shown in the figure. The signal x of n is at n equal to 0, its value is 2. At n equal to 1, its value is 1. At n equal to 2, its value is 0. Similarly, sorry, at n equal to 0, its value is 2. At n equal to minus 1, its value is 1. At n equal to minus 2, its value is 0, and so on. Similarly, at n equal to 1, its value is 0. At n equal to 2, its value is 1. Now, we want to find out y of n, which is equal to x of n by 2. We know that x of n by 2 um, seal off. It means that the value of n by 2 should be sealed, and that index should be used to find x of n by 2. So from this we can see that the given signal, from the given signal x of n by 2 or y of n can be obtained as given. Say at n equal to 0, the y of 0 will be equal to x of 0, which will be equal to 2. At n equal to 1, y of 1 will be equal to x of 0. So this should also be equal to 2. So at n equal to 2, y of 2 will be equal to x of 1. So this would be equal to 0. Similarly, at n equal to 3, that is y of 3, its value is 0. Similarly, we can show that y4 and y5 are equal to 1. Similarly, for n less than or equal to minus 1, we can show that y of minus 1 is equal to y of minus 2 is equal to um, y of minus 1 will be equal to x of minus zero point 0.5 seal, which will be equal to x of 0. So this would be equal to 2. So y of minus 2 equal to y of minus 3 equal to minus 1, and y of minus 4 equal to y of minus 5 equal to 0. From this, we can plot y of n as shown. The y of n has a value of 2 at n equal to 0, 1 and 2. So at n equal to 0, 1 and minus 1. At n equal to 2 and 3, the value of y of n is 0. At n equal to 4 and 5, the value of y of n is 1. Similarly, for at n equal to minus 2 and minus 3, the value of y of n is 1. Sorry, this should be 1. And at n equal to minus 4 and minus 5, the value of y of n is 0. There is a discrete time causal system which is represented as y of n is equal to x of an truncated. This is for n greater than or equal to 0, and x of n by a truncated. This is for n less than or equal to 0. It's also given that the system is causal. We have to find the range of a for which this condition would be satisfied. Here T implies the truncation. So if the system is causal, the output y of n should depend only on past x of n. For this to be satisfied, say for n greater than or equal to 0, a should be less than 1. That is, 0 should be less than or equal to a less than or equal to 1. If and only if this condition is satisfied, the if we take the condition for n greater than or equal to 0, system would be causal. Now similarly, if we take the case n less than or less than 0, in this case y of n is equal to x of n by a truncated. Here as a is between 0 and 1, sorry, as a is between 0 and 1, y of n would depend on past x of n for all values of n. From this we see that the given system would be causal if 0 less than a less than or equal to 1. Now let us consider another discrete time system. Y of n is equal to x of n for n greater than or equal to 0, and x of n plus 1. This is for n less than or equal to minus 1. We have to find if the system is linear, time invariant, causal, stable, and memoryless. And invertible. We see that the given system satisfies superposition principle. From this, we can say that the given system is linear. Also, we can see that the delayed version of input y of n minus n naught is not equal to the output due to delayed version of input. From this, we can say that the given system is not time invariant or it is time variant. Also, we see that for n less than or equal to minus 1, the output at any n depends on future x of t. From this, we can say that the given system is non-causal. As the system is non-causal, it is not memoryless as well, or the system has memory. For checking the BI/BO stability, if the input is bounded, that is mod of x of n is less than or equal to bx, we can show that mod of y of n will also be less than or equal to bx. As the system input is bounded for every n, the output would also be bounded. From this, we can show that the system is BI/BO stable. Also, to check the invertibility of the system, let us consider for x of n greater for n greater than or equal to 0. For this case, the inverse system would be x of n is equal to y of n. Now, if we consider n less than or equal to minus 1 case, in this case, the inverse system would be x of n plus 1 is equal to y of n, or by replacing n by n minus 1, x of n is equal to y of n minus 1 is the inverse system. From this, we see that the given system is invertible and the inverse system is x of n is equal to y of n for n greater than or equal to 0 and y of n minus 1, this is for n less than or equal to minus 1, is the inverse system of the given system. There is a continuous time system whose transformation is given as y of t is equal to integral minus 2 to 2 t by 2 x of tau d tau. We have to find if the system is linear, time invariant, causal, stable, and memoryless. We see that the given system satisfies superposition principle, that is, linear combination of inputs would give linear combination of outputs. From this, the given system is linear. Also, we see that the delayed version of output y of t minus 2 naught can be written as integral minus 2 times t minus t naught to t minus t naught by 2 x of tau d tau, and the output due to delayed version of input is can be written as integral minus 2t to t by 2 x of tau minus t naught d tau. Now, upon converting the integration to tau minus 2 naught equal to p, we get that this can be reduced as minus 2t minus t naught to t by 2 minus t naught x of p dp. This is not equal to y of t minus t naught. So the delayed version of output is not equal to the output due to delayed version of input. So the system is time variant. Also, we see that the output y of t depends on future x of t. So the system is non-causal and hence it has memory. To check the stability, if we assume mod of x of t is less than or equal to bx, it can be shown that mod of y of t will also be less than or equal to by, where bx and by are finite. From this, we see that the system is stable in BIBO sense. Now, we can see that the given system is linear, time variant, non-causal, has memory, and is BIBO stable. Now let us consider another system y of t is equal to e power minus mod x of t. We have to check if the system is linear, time invariant, causal, stable, and memoryless. Now we see that the given system doesn't satisfy superposition principle, that is, linear combination of inputs wouldn't give the linear combination of outputs. So the system is linear. Also, we can see that the delayed version of output, that is y of t minus t naught, is equal to the output due to delayed version of input. So from this we can see that the system is time invariant. We also see that the output y of t for every t depends on present x of t only. From this we see that the given system is causal. As the output depends on present x of t only, it is memoryless as well. We can also show that if the input is bounded, that is mod of x of t is less than or equal to bx, mod of y of t would be equal to, is also less than or equal to e power minus bx. As bx is finite, e power minus bx is also finite. From this, we see that the given system is stable in BIBO sense. From this, we see that the given system is nonlinear, time invariant, causal, memoryless, and BIBO stable. That is, stable in BIBO sense.